We're continuing on here, chapter 12. We're pretty much done with it. Just talk about a couple things, I think. But last time we got into, again, really the temperature rate relationship. So we have the Arrhenius equation, our guy here, where we have a couple of rate constants. And obviously, we could use this formula as we talked about more as like sort of a calculation type formula. If you have 2 points really along that line that really is from sort of this formula, which is our y equals mx plus b. Ideally, that is more the graphical version of this. And if you did have kind of 2 points on that line, you can use the mathematical equation. Again, you could solve for anything from temperatures, activation energy, or even rate constants, obviously, if you're given enough information. Ultimately, what we saw and what we talked about is, again, the relationship of temperature and the rate is typically speaking, as we increase the temperature, we will see an increase in the rate of the reaction. And vice versa, if we decrease the temperature, we will see a lowering of the rate or the slowing of the rate. For example, I think in that we did an example where we had like a 10-degree difference sort of shift, and we did see it almost drop actually about halfway from where it started in terms of its rate. So the idea there is again that when we do increase the temperature, is that activation energy hill that everybody has to climb. So with the increased amount of temperature and energy, there's a greater proportion that can really kind of get up and over to the other side, and that's going to cause the reaction really to really proceed faster. And vice versa, obviously, if we lower the temperature, we're going to have less that's going to get to the other side. We then talked about reaction mechanisms. And the idea of reaction mechanisms is not all reactions will take place in a one-step process. Again, it may be multiple steps along the way. And these sort of multiple steps along the way are what are referred to as elementary steps in the mechanism. And they try to a mechanism sort of explain how a reaction takes place, the steps that occur as reaction is taking place. And remember that there are certain things a lot of times in a mechanism that are intermediates, and those are things that are sort of made early on in the mechanism and then gets sort of used up by the time the reaction's over. So if we were to add these together, again, anything on opposite sides of the arrow will cancel. And obviously everybody on the left will stay on the left. Get my letters right. There you go. And everybody on the right will stay on the right. In this case, C and D would be intermediates, as they get made early on in the mechanism, but gets used up in a sort of step after that. Remember that for something to be an intermediate, it cannot be in the overall reaction. So it has to sort of really disappear by the time the reaction is done. That is why we have sort of reaction mechanisms. For example, when people do certain reactions, they do note the presence of certain, say, chemicals along the way. But is not necessarily there at the end of the reaction. So that would again imply that the reaction doesn't take place in a one-step sort of fashion. There's multiple steps along the way. There is usually in a mechanism what's known as the rate determining step. That is the slow step in the mechanism. That is the one that really determines the rate of that reaction. The importance of identifying the rate determining step is it should have the same rate law as the rate law found experimentally. So that's one way you can identify which step of the mechanism is, say, the rate determining step is if they give you the experimentally found rate law and one of the elementary steps has a rate law that matches it, then that would be your rate determining step. The other way, which is much easier, is a lot of times they will list slow and fast, and whichever one's listed slow would be your rate determining step. Remember that the only place really in kinetics where you can use the coefficients to write a rate law is in these elementary steps when you're doing a mechanism. So you can come up with a rate law for each of these sort of steps. If this was step 1 and step 2, again, by just using the coefficients that there are in that particular equation. The other type of mechanism problem that we finished up on last time was one more like a proof type problem. They kind of identify the rate determining step. You write the rate law for that step, and it has sort of an intermediate in it, and you can't really compare that rate law to the one found experimentally without doing some like extra work to kind of substitute out the intermediate in that rate law, and then you can compare them. And again, as we saw, if you just straight compare the rate law with the intermediate to the one found experimentally, they pretty much will never match. But you really are not making a fair comparison, so you do have to get rid of that intermediate so that you can compare sort of like apples to apples in that situation. Any questions on any of that stuff there? All right, so one last one here. Why don't you give this a go? Determine the overall reaction. What's the rate determining step? What should be the rate law here and mechanisms? So we definitely can write rate laws for each of these. So for the first step there, the rate would equal K A times B2. For our second step there, the rate would equal K, A, and B. Again, because this is a mechanism, we can write a rate law for each of these steps using the coefficients and obviously just the reactants. Here we can get the overall reaction by adding these together, and it looks like B will cancel, and I think that is it. That's going to give us a 2A plus a B2 goes to 2AB in this case, yeah. So this would be our overall reaction, obviously. We know just from the way it's listed that this guy right here, right, should be our rate determining step as it's listed as the slow step. So step number 1 here should be that. And because step number 1 is the rate determining step, that means that the rate law that we have for that should also be the rate law that is for the experiment as well, right? So that should have a matching one. In this case, it actually does contain everything in the overall reaction, right? No intermediates or anything in there, so not to worry about that. And other than that, I think that is it, I think. Yeah. Any questions on that B being our intermediate? So this is again a sort of third type of mechanism type problem where obviously you could get that type of information from it. Any questions on any mechanism type of situation? Or which one now? For the overall reaction? No, so we're just going to be adding, are you talking about this guy right here? Yeah, so we're just basically adding everything on the left-hand side together. So if you did it kind of longhand, you basically have this. So basically you have A and A, which basically becomes 2A, right? What do you have them together? Yeah. No. So basically the rate is just yeah, so remember that the slow step will have the same rate law as the overall reaction or experimentally found one. And also remember that because technically speaking, this is the overall rate law for the entire reaction, that the orders here don't necessarily match the coefficients in the overall reaction. Yeah. So again, those orders would be found experimentally. So the only place where the sort of orders and the coefficients will be the same is when you write the rate law for the elementary steps in a mechanism like we did here. So that's why these guys will have the same as coefficients. But when we look at the overall reaction and the overall rate law for the reaction, they not necessarily relate to each other that way. Other questions? Okay. All right. So lastly here, a catalyst, as we've sort of touched upon in a few spots along the way, a catalyst is a substance that's really added to a reaction in a lot of cases to increase the rate of the reaction. Once again, a catalyst is not considered a reactant. is not considered a product. It is usually there again just to sort of facilitate the reaction happening more efficiently is a good way to think about it. It actually does not get used up. Does not get used up. We typically, again, in equations, find catalysts written on top of the arrow. A lot of times is where we sort of see them in equations written. And ultimately, what they do again is really find a more efficient sort of pathway, if you want to think about it in that sense, for that reaction to take place. So again, in a uncatalyzed reaction, you may have some gas molecules that are flying around. They got to fly around and try to find each other, to sort of combine and start reacting. Now, you could add like a catalyst where it will perhaps attract those gas molecules closer to it. And by doing so, that's going to put those guys in much closer contact a lot quicker than it would if they're just kind of flying around trying to find each other. They're all going to kind of head towards a central location. The result of that is it's going to probably increase the number of collisions and obviously get more reactant molecules starting to react in that case. So by finding that efficient pathway, ultimately what a catalyst does when we look at our reaction diagram here, our energy diagram, is it's able to basically lower this activation energy. So by finding an alternative pathway, the end result is the activation energy is lowered. That also helps increase the number of molecules that have enough energy at that point to get to the other side, again, because it's a lot more efficient in doing so. That again would increase the rate of the reaction. Instead of these reactants having to climb this giant hill to get to the other side, it's just going to be this smaller hill. And again, more going to be able to get up and over basically to the other side there. And an increase in the rate of the reaction will be seen. So typically we see a decrease in the activation energy, an increase in the rate constant, indicating that we get a much faster reaction. There are some catalysts that are negative catalysts, and they're used actually to slow down a reaction. But I would say probably 99.9% of the time when somebody's talking about a catalyst, usually they're talking about it in the aspect of speeding up the reaction. But there are certain things that you sometimes can use to slow things down. And that's sometimes referred to as a negative catalyst if you're using a catalyst to kind of slow things down rather than, say, a positive catalyst, which would sort of speed things up. In addition, catalysts can be either homogeneous or heterogeneous. So just like in mixtures, heterogeneous means you see different phases and stuff like that. And that's sort of the same idea. The reactants and the catalysts are in different phases. So like the Haber process for ammonia synthesis, the making of nitric acid are what's in your catalytic converters. In your car, your catalytic converters have a bunch of metals in there, right? They're solid, right? And gases and stuff go through there. And obviously, it reduces some of the pollutants along the way. But the catalysts to those reactions are solids versus, say, gases that come through there. They also could be homogeneous catalysts, and that's when the reactants and the catalysts are in the same phase. Usually a liquid, we could have an acid catalyst or a base catalyst. And that a lot of times for an acid catalyst, you'll see H plus sort of written on the arrow, and that indicates an acid catalyst. By the way, technically speaking, the reaction we're doing in the lab, the HCl is an acid catalyst, basically. Even though we're sort of treating it like a reactant, it actually is an acid catalyst in that particular reaction that we're doing. And as you can see, the HCl is in the same phase as everything else that's reacting, the triiodine and all that other stuff that you're putting in there, the acetone, they're all in the same phase. So that's very common. Again, a lot of acid catalysts are base catalysts, help kind of put everybody in the right sort of pH environment to facilitate that reaction to occur perhaps a lot more efficiently than it would in an, say a neutral environment or a base environment or an acid environment. Here's sort of an example of the ammonia synthesis, and as you can see, there's a lot of solid catalysts that are used. And once again, you can kind of see what I was saying before. These are our gas molecules, our nitrogen and our hydrogen flying around. And without the catalyst here, they would just be flying around trying to find each other. But again, with this sort of solid catalyst, it sort of directs all the gas molecules towards the catalyst. And actually, the catalyst in this instance actually helps a little bit with kind of the breaking apart of all these guys and the reassembling that sort of occurs there. And then they can kind of reassemble and go off. So again, it just provides sort of a more efficient platform for that reaction basically to take place than it would if it was not there. And that sort of efficiency, if you want to think about it, is what kind of allows it to sort of occur a lot faster. This is nitric acid formation. Actually happens in a few step process here, but they do use a platinum wire as a sort of a catalyst to do that and make some NO and some NO2, which can combine with some water to make some nitric acid and nitrous acid. And actually, that nitrous acid being formed can also break down and produce some more of the NO2 that can then go back and make some more nitric acid. So it makes it quite a more efficient process for that reaction to take place. And there's our cars, like we just talked about. If you do have a catalytic converter in your car, a lot of precious metals, solid metals are in there, which is why, right, people chop, take your catalytic converter, right, out of your car for the metals that are in there. And I always love this part here because they used to do that a lot out here in our parking lots, believe it or not. But they would send out like emails. If you see somebody with like a circular saw walking through the parking lot, you should actually tell somebody. So it's like, yeah. So that's why again they will actually still obviously your catalytic converters because there's a lot of precious metals that are in there. The purpose of them is obviously as it goes through there to your exhaust and from your engine as it's doing the combustion reactions, it goes through each of those things to kind of clean up those guys from releasing some unburned hydrocarbons and pollutants. And obviously what comes out is a little bit more better for the environment than, if they weren't there. All right. That is it for chapter 12. We were off then to chapter 13, I think here. Give me a second here. Okay, we are off to chapter 13, and now I can officially say this class is going to start now, I suppose. That was a nice warm-up chapter, I suppose, but now it's all about equilibrium, and we're going to talk about every type of equilibrium you never want to know about. And by the time we're done, you'll go, I'm not very sure I want to know any more about equilibrium. But you talk about really what equilibrium is and what type of reactions they involve. Equilibrium reactions really do involve a certain type of reaction, and these are reactions that basically are reversible reactions. And they typically will have, again, these arrows that are heading in both directions. And that means that there is, again, what is considered a forward direction, which is, again, going from our reactants to our products. At some point along the way in this type of reaction, you will actually make enough products that the products will decide we would like to go back the other way. And the products will start to combine with each other. And we will actually get the reaction heading in the opposite direction from products to reactants. And that, again, is what is known as the reverse direction in the reaction. This process will continue until chemical equilibrium is reached. And sometimes people have a really misunderstanding about what chemical equilibrium really will mean. And it's not that bad of an idea because it has the word kind of like almost like equal in the name. So people oftentimes think that when it reaches chemical equilibrium, you got like equal amounts on both sides of the arrow. And that is not what it means. It is actually talking about what we talked about in the last chapter. It is actually talking about the rate of the reaction. And what it is talking about when it reaches chemical equilibrium is the rate of that forward direction of that reaction will equal the rate of the reverse direction. So what we're talking about is essentially just as fast as it makes products, those guys are going to combine and shoot back the other way just as fast as they were made. So what that essentially does when something reaches chemical equilibrium is it will lock everybody into place in terms of where they are, in terms of their concentrations, or pressures if you're dealing with gases. So it basically just locks everybody into place at whatever point they are in terms of concentration or pressures, and they won't change because just as quick as it goes to the products, it's going to come back. So it's like lose a little, make a little, lose a little, make a little. So everybody's able to basically maintain where they're at. Again, doesn't mean that you have the exact same amount of everybody on each side, but it just means that they're able to maintain that. So for example, if we had this reaction and initially we had, say, 4 molar of this guy and 3 molar of this guy and nothing of this guy. When it reaches equilibrium, maybe we got like 2 molar of this guy, 1 molar of this guy, like 3 molar of this guy, and maybe 4 molar of that guy. When it reaches equilibrium, what it means is these guys' concentrations and these guys' concentrations will pretty much just stay there. They're not going to change unless you do something to screw up the equilibrium, which we'll talk about. But if you don't do anything to screw up the equilibrium, they will just stay there and just continue basically to keep and maintain basically the reaction. Again, you can see it doesn't necessarily mean that they have equal molarity on both sides or anything like that. But overall, they'll be able to maintain their sort of concentrations. Now, when we look at a reaction that is in equilibrium, you could look at a reaction at equilibrium, and for example, if we had, say, this beaker and this reaction we did, and it looks like it's over, maybe it turned red or something like that. And you look at the beaker and go, wow, that's nice. Nothing much seems to be happening anymore. The reaction's over, right? And let's just say that this reaction was that one that, say plus B goes to C plus D. Now, although it may look like there's nothing happening in the beaker on sort of the big level, the macroscopic level, there is a lot of activity that's actually happening. If you like super zoomed in, you will see a lot of A plus B going to C plus D. You'll see a lot of C and D continuing to react. So even though the reaction may look like it's done, if you're just looking at it like a beaker or something like that, there's a lot of activity that's continuously happening sort of behind the scenes, if you will, to keep it like that, because again, it's constantly going back and forth, this sort of reaction to maintain their concentrations as you go through it. So that's why we kind of say on the macroscopic level, it's static, like, okay, it's done. There's nothing else happening. But again, if you were to sort of zoom in on the microscopic sort of view of it, there's a lot of activity. We have reactants going to products going to reactants. They're just doing it at the exact same rate. So again, that net doesn't make anything change, but there is a lot of activity that's continuously happening in an equilibrium system. And when we look at this reaction, which is our N2 plus our H2 makes a little bit of ammonia here. I'll balance it like I'm a chemistry person. There we go. Wish a 3 maybe. So at the very beginning of this reaction at kind of time 0, it's pretty much all reactants. That's all we got going on. We only have H2 and N2 in this case. We have none of our products being formed. Remember, in order for our products to be formed, the first thing that would have to happen in this situation is the forward reaction would have to occur, right? So we would have to kind of kick off the forward reaction. The reason the forward reaction should occur is a very simple explanation. It's the only thing there, right? So you have a lot of reactant molecules. They're going to be able to find each other and start making your products, right? So just the availability of those reactants being present will cause the forward reaction in this case to kick off. And the result of that is we would have to use up some of our reactants, but at the same time, we will start to see some of our products starting to be made in this case, right? And we're going to start to build up some products that at some point we will get a sufficient amount of products that will actually kick off the reverse reaction to occur. So at some point, you will build up enough products being available that they can actually start reacting themselves, and you'll actually start to see the reverse reaction happening. You could kind of see where that might kick in, which is we get a nice little peak of products happening here. We also have a fairly steepish decline of reactants, but now this reactants are starting not to decrease as fast, right? And that would indicate that we've made some products and perhaps we now have the reverse reaction starting to occur, right? We got some of those guys going backwards in the other direction. This process will continue. We'll have the forward direction going, we'll have the reverse direction going until at some point it will reach chemical equilibrium. And that is the point where, as we just talked about, when it reaches chemical equilibrium, it will essentially lock everybody into place in terms of their concentrations. That is represented on a graph as a flat line, yeah? That basically means the concentration is not changing, right? Flat line and basically a flat line. Concentration is basically the same all the way through there. If I could draw straight lines, that would be straight. They would be the same, it's not changing. That is where chemical equilibrium reaches. So if you look at a graph of reactants and products or concentration over time, there should be a point where they all start to flatten out basically and run a plateau line straight across. And that means that their concentrations are no longer changing. And that is where chemical equilibrium basically has been met. And that is where the rate of that forward reaction will equal that rate of the reverse reaction that essentially, again, will lock in their concentrations. We could also see here from this graph that all the concentrations of our reactants and products, again, are not the same values, right? They're different values, but they're all constantly staying the same, whatever value they're at. So again, that's the idea of equilibrium. Not that we equal out everything on both sides, but basically because the rates are going to be equal to each other, it just locks everybody into place and they will be able to maintain that over a period of time and keep maintaining it basically as time goes on. Any questions on that there? Now, here initially in this reaction, if we look at water plus a little carbon monoxide, making some hydrogen gas and carbon dioxide, initially we could probably assume again that there's no products present. So initially we would account for a lot of activity happening here because they're going to be able to find each other. And again, that will kick off that forward direction. At some point, we will start to see a buildup, an increase in these guys' concentrations. And we also see a decrease in these guys' concentrations. And by the time they get to a sufficient amount, that will cause the reverse reaction to start to get into place. And again, they will continue until those rates will basically equal each other and it will reach chemical equilibrium. So that is basically where you can see graphically that a reaction has reached equilibrium. Wherever you see everybody's concentrations pretty much plateau out and become like a straight line. Now, let's say we have this reaction in a flask and we decided to add more water to it. How would the concentrations of everybody be affected by that? So take a moment and think about it. So would they increase? Would they decrease? Would everybody stay the same? Take a think about what might happen in this situation. Okay, so let's take a look and see. We're going to add water in this case, or really steam, I guess. That is right here, right? That is a reactant. So in this particular case, this would be like adding more reactants. So would that cause this reaction to maintain the same sort of rate? Will it cause to cause the forward reaction to begin? Will it cause it to cause the reverse reaction begin? What should happen in this case? What would increase the rate of something in terms of concentrations? If I increase concentrations, would I expect the rate to increase or decrease? How does a reaction occur? Somebody's out there, right? How does a reaction occur? You need two things to happen, right? They need to hit each other, right? And they need to hit each other with the right amount of energy. So if I have more of something, would that cause more collisions or less? More, right? So in this particular case, right, if we add more water, which is a reactant, we would expect the more availability for these two guys to find each other, right? And in this case, that actually should cause the forward direction to kick off, right? Because we're going to have now more reactants than products. So they're going to be able to find each other a lot easier than our products. And that should cause actually our reactants to go towards products and the forward reaction to occur. That means that the concentration of H2, should it go up? Should it go down, or will it stay the same? H2 should go up, right? Because if I'm doing the forward reaction, that means I'm making products, right? So we should see an increase in the products. CO2 should go up as well. It's also a product, right? So we should start to see an increase in product formation. How about CO? What should happen with that? It should go down. The only way to make products is the two reactants actually has to come together, right, to make those products. So that's going to cause a decrease in the reactant concentration. What about H2O? What happens with it? It's kind of an interesting thing. It definitely is going to go up, and it's only going to go up because you added more, so you artificially made it go up. But after it goes up from your artificial adding, it then should start to go down, right? Because it's going to be needed with the CO to react to make our products. You might even see with water, you end up with more than you started with only because you added more to it. So you kind of spiked it, but then it will start to come back down as it reacts with the other reactant and make our products. Question on that there. All right, then you think about this one. If we add more H2, what will happen to everybody's concentration? Okay, so we have this at equilibrium, which means basically right at this point, by the way, the rate of the forward and reverse direction are equal to each other. It's at equilibrium, basically is what it says, right? So we decide to add more H2 to it. By the way, you're going to now screw up the equilibrium. That's why we're going to see some type of change occur. This is one way you can screw up an equilibrium, is to add some more stuff to it. Kind of messes up the flow of back and forth at the same rate. In this case, should the forward reaction, reverse reaction occur? What do you think? It should be, we are adding more products, which means the availability of our products now should be greater than our reactants, and that should cause the reverse reaction to occur, right? That's going to cause those products to combine a lot easier than the reactants because there's just more of them. And that will cause the flow from the product side to the reactant side and the reverse reaction to take place. That again means in this case, water actually should go up as it's increasing. And CO should actually increase as well because now we're making really our reactants because we're heading in that direction. We would see again a decrease in the CO2 as it is needed to make those reactants. And in case of H2, we would see really the same things we talked about with water on the previous one. It definitely will increase because you added it, but then again, you should start to see it come back down as it starts to react to cause the reaction to head in that direction. So it'll kind of peak and then sort of come back down as well. So as we'll talk about later on in this chapter, this is really one thing that you can do to a system that's at equilibrium to screw it up is, change concentration. There are other things that we'll talk about later on in the chapter, like changing the temperature and doing some other things that can change the pressure or volume. These are all things that can affect the system, a system that is at equilibrium. Any questions on that there? All right, so let's talk about the relationship here of a equilibrium reaction. And if we have this reaction here, N2O4 goes to 2NO2, we could write a relationship which is known as capital K, really just K, but it is a capital K, not to be confused with, for dramatic drawing purposes, lowercase k, which is our rate constant that we used in the previous chapter. This class is really brought to you by capital K, which is the equilibrium constant. Yeah, we will learn about all kinds of equilibrium constant. The equilibrium constant is a constant value for a reaction at a specific temperature. So as long as you do not change a temperature, there is a relationship for that reaction that will always give you the same number, which is the equilibrium constant. To calculate the equilibrium constant, we actually take basically the concentration of our products over the concentration of our reactants. So it's always products over reactants. Unlike in kinetics, in equilibrium, we absolutely use the coefficients as the exponents. So we take the coefficients as the exponents. Obviously here, that's a 1. And much like most things in chemistry, we don't really write the 1. We just leave it blank. So again, if you don't see anything written, it's assumed to be 1. And again, if the coefficient is 1, we leave it there. In general, you could take the concentration of the products over the concentration of the reactants to get your equilibrium constant value here. The good news about equilibrium constant, I guess, in a sense, is it is actually one of the few things in chemistry, no units, just a number. So it basically is just a number, no units associated with it. But it does give you some important information about what's going on in a particular reaction. So for example, if I had a large value of K, would I mainly have, when I reach equilibrium, would I mainly have reactants or products if I had a large value of K? It would be products, right? Because just mathematically speaking, large number divided by a small number gives you a large number. So if you see a large value for K, what that tells you is when that system reaches equilibrium, you will mainly have products. And obviously vice versa, if you have a small value of K, that means that you would actually have more reactants when you reach equilibrium. Again, larger number on the bottom, smaller number on top gives you a smaller number for K. What is considered a large value or versus a small value? What's considered a large value is the large value of 1. Yeah, anything above 1 is considered large. Anything less than 1 is considered small. So 1 is kind of your right there number. By the way, when we do products over reactants, and I'm sure we talked about the little bracket, that does mean, again, concentration and molarity is usually what we're talking about there. This is also sometimes referred to as a specific type of equilibrium constant when you take the concentrations of the products over the reactants. That is sometimes referred to as Kc. I'm assuming C means concentration, so that will go with that. So Kc is an equilibrium constant where you take the concentration of the products over the reactants using the coefficients as the exponents. Because this is an equilibrium constant, that means that only equilibrium concentrations can go into that expression. You can't just put in initial concentrations. They have to be equilibrium concentrations to go into here to actually solve for a particular number. Any questions on that there? So again, as I mentioned before, that equilibrium constant value will definitely give you some good, important information as to what you should expect to sort of be there when you do reach equilibrium. Now, let's take a look at this here. So we got this reaction here. We got Mickey plus these two guys makes these two guys a Mickey after a long day. upside down. With a K value of 25, would we expect this equilibrium to have mainly reactants or products when we reach equilibrium? It should be products, right? So again, that is considered a large value of K. That means that we should have a lot more products than reactants when we do our products over our reactants. Now, there is obviously, as we will definitely see as we go through these different chapters, there is different degrees of sort of large and small. There are some that are really, really large, like times 10 to the 36, 54, pretty big numbers. There are some that are really, really small values of K, like the times 10 to the minus 34 or something like that. This is a really, really small value. And there's ones that are, in the between. So there is a large range of equilibrium constant sort of values. Now, the equilibrium constant value will always be the same number, hence the name constant, as long as you do not change the temperature. And this is something that troubles people sometimes, which is, for example, maybe I go back here to this here, use this page. Now, what I mean by this is this value will be the same as long as the temperature is this constant. So for example, if I did this reaction and I did like 3 different experiments, right? And I kept the temperature at 25 degrees Celsius. And in experiment 1, I decided to start with 5 molar this guy, 4 molar this guy, 0 and 0. In experiment 2, I decided, hey, let's do like 2 molar this guy or that guy. And in experiment 3, I decided, let's just start with like 3 molar this guy and 4 molar this guy. When I let these reactions all go, and again, the temperature in all 3 of these are going to stay at 25 degrees. If I let all 3 of these reactions go to equilibrium, will my K value be the same for all of them? The answer is yes. Even though you started with all reactants, you started with a little bit of everybody, you started with all products and no reactants. When they reach equilibrium, the ratio of the products to reactants will always equal the same number as long as the temperature doesn't change. Sometimes people think, wait a sec, I started with like 2 in the second one, but 5 in the first one. I should get a different number, right? Because we started with different amounts. And it doesn't matter because the ratio of those products to reactions will be the same. Here's a very simple example to help you understand that. If I take 8 and I divide it by 4, what do I get? If I take 4 and I divide it by 2, what do I get? If I take 2 and I divide it by 1, what do I get? They're all different numbers, right? Different numbers, but the ratio of those numbers all come out to the same. And that's what happens here. In this situation, even though we started with more reactants in one, less reactants in another, a little bit of everybody going on, when that thing finally reaches equilibrium, the rate of the forward reaction and the reverse reaction equals each other. Those proportion of reactants and products that you have to each other will also end up at the same number. Now, if I did these exact same 3 reactions, not at 25 degrees, but I did it, say, at 50 degrees Celsius. So I ran all 3 of these experiments, 1, 2, and 3. And I kept all 3 of those experiments, once again, at 50 degrees Celsius. And I calculate the equilibrium constant at 50 degrees Celsius for all 3 of those experiments. Will they be the same? They will be the same. Again, I didn't change the temperature. When I look at the equilibrium constant, say the average value that I got at 50 degrees Celsius and 25 degrees Celsius, will they be the same? They will not, because that's the change in temperature we're talking about. So when we talk about as you change the temperature, the equilibrium constant changes, we're talking about the comparison between doing the same experiment, say at two different temperatures, will yield you two different equilibrium constants. But if you move your temperature from one temperature value to the next and continue to run all those experiments at the same temperature that you change it to, you will still have a constant value. But in comparison to the other temperature, it will be a different value. Any questions on that there? All right. So again, that's a very common mistake that sometimes people have, which is like and it makes sense sort of logically thinking about it that, hey, I like started with way more in this experiment. There's no way it should all come out to the same equilibrium constant value. But again, it will, as long as that temperature remains constant for both of those experiments that you did, you should end up with the same one. We will actually do this down the road here in a few experiments. You will do an equilibrium constant of like a room temperature and a hot temperature. And all the ones at room temperature should be about the same. All the ones at hot temperature should be about the same. But comparison of the hot temperature and the room temperature K will be different values because they're at different temperatures. Any questions on that part of it there? Okay. All right, so let's talk about writing equilibrium expressions. As we did a second ago, we basically take our products over our reactants. And when we do it with concentration, as I mentioned, that is Kc value. But in this particular reaction, we actually have gases. And when we think about gases, we think about PV equals nRT. More specifically, we think about pressures. So you can also write an equilibrium constant that deals with pressures. It works the same way. You take your products over your reactants. So in this case, that would be the partial pressure squared of NO2 divided by the partial pressure of N2O4. Surprisingly enough, this is another K value added to our giant list that we will have by the time we're done. We're only like 3 slides in and we have 2 of them already. So Kc and Kp, Kp meaning pressure. I will say this, that typically speaking, when you're dealing with equilibrium and you're doing something that involves pressure, especially a calculation that involves pressure, what unit do you think you should use? ATM, yeah, is usually the unit that you want to use if you're doing some type of calculation with equilibrium that involves pressure. 1 ATM, as a reminder, right? 760 torr, 760 millimeters of mercury. Yeah. So sometimes we may be given pressures rather than concentrations. It works the exact same way. The Kp value and the Kc value in a lot of cases will not be the same numerical value. They actually can be in certain cases, but usually they're different numbers. But they do still tell you the same thing. So if you have a large value of K, P, that means you will mainly have products. And if you have a small value of Kp, you will mainly have reactants. One of the important things to remember with equilibrium constants, and I'm not exaggerating, we will have Kc, Kp, Kw, Ka, Kb, Ksp, Kf. I always keep going. But we'll have all these K values. They're all just equilibrium constants. They're all basically the same idea. They're all products over reactants. They're all equilibrium constants. They tell you basically the same thing here. So there is a way that you can go between Kc and Kp if you needed to. And you can do this by taking this equation. The Kp value, by the way, again, still an equilibrium constant value, which means it doesn't have units, will equal Kc times RT. These are actually like our gas law. So it is the same R value that you would use in the ideal gas law, 0.08206. Or if you learn the rounded version, a lot of people teach these days, I suppose that one right there. And much like everything else, our T here is in Kelvin. Yeah, so that's in Kelvin, right? Times are taken to the delta N. Delta N is the change in the number of gas molecules. You find that by taking the gas molecules on the product side minus the gas molecules on the reactant side. it is as simple as just grabbing the ones with G's next to them, right? And then subtracting those guys out. Now, this is really important, the delta N part, that you do it correctly. So for example, if I had 2A goes to C as my reaction here, my delta N here would be what? Is it 1? Is it -1? Doesn't matter. Well, delta N in this case is our products. That's a coefficient of 1. So that's 1 minus 2, which is -1. That is what it should be, because it does matter if you're not sure, because when you go into this part of the equation, if I have it RT to the 1 versus RT to the -1, mathematically, is that a different calculation? It is. That's like 1 over it, right? So you do not want to just take the difference, which is a very common thing that people do. They just take the difference. If it is a negative difference, that's really important in terms of the calculation part that you need to do, and you will screw up the math. So make sure that you always go products minus reactants. It's simply just the coefficients will tell you how many moles you have, and it is only things with obviously gas next to it, or the gas state. In order to obviously have a Kp value, you obviously do need gases there. So if you don't have gases, you typically will not have a Kp value, because there's no gases, there's no pressure basically associated with it. Any questions on that there? It's liters times atmosphere divided by Kelvin times mole. The good news is, if you're going to use it for any of these, they actually still don't have units. So, but that's what it is. It's liters times atmosphere divided by Kelvin times mole. Other questions? So if we look at what is referred to as a homogeneous equilibrium, and homogeneous equilibrium basically means that everybody's in the same phase, and we do our products over our reactants. Here's our acetate, a little acetic acid, some hydronium ion. So we take our products over our reactants here. Now, one thing when we write equilibrium expressions is we typically don't put anything in there that really won't affect the equilibrium. Now, water's concentration is pretty much going to hang out constant the whole time. So typically speaking, we would not include it in our equilibrium expression. And for this particular reaction, this would be the proper equilibrium expression. I will jump a couple of slides and just tell you right off the bat that typically speaking, when you write K, there are two things that you typically do not include in the expression. You do not include pure liquids like water, because their concentrations pretty much remain the same. And as we will later see, we do not include things that are solid, because if they are solid, they're basically just sitting there, not doing much. They're just a solid. That means that we pretty much have two things that we do include, and that is anything that is aqueous, like a water environment, like a solution, and anything that's a gas. So these are the two things that we include in the equilibrium expression: aqueous and gas. Anything that's a liquid or a solid, we basically leave out. As I mentioned before, typically speaking, we do not have units associated with it. So just a number, that's all you have to worry about. All right, so write the Kc and Kp if possible for each of these, see what you come up with. Excuse me. All right, so let's take a look on the first one here. So we'll start with our Kc. So again, it's going to be products over reactants. So that would be the concentration of NO2. Again, we do need to take it to the fourth power because of the coefficient. That would be times our O2. Again, its coefficient is 1, so we don't have to put anything. That's all of our products. We'll divide it by our reactants, which is the concentration of N2O5, we also again need to square it because of the coefficient there. So that would be our Kc expression. Any questions on that one there? Can I do a Kp for this one? I can. They're gases, so we can write a Kp expression. It will look pretty much identical to the Kc, except instead of concentrations, it's going to be partial pressures of NO2, also still to the fourth. Partial pressure of O2 divided by the partial pressure squared here of N2O5 in this case. Question on that one there. Clearly on the left there, we would use molarity. On the right there, probably something like atmospheres is what we would be popping into there if we had some numbers, right? Again, they would have to be, by the way, when we're talking about Kp, just like Kc or any of the equilibrium stuff, they would have to be equilibrium pressures to go into there. Again, not initial pressures or anything like that. For our bottom one here, we're going to go Kc is equal to the concentration of H3O plus times concentration of F minus divided by the concentration of HF. Do I put the water in? I do not, because it is a pure liquid. So it is left off as it will be constant. And that would be our Kc value in this case, our expression. Can I write a Kp in this case? I cannot either because there's no gases, right? So there's no way to kind of write a Kp. So you do need some gases to do that. Now, what happens if I had like, what if I had something like this? What would the equilibrium expression be? Would I include this, which is a solid? No. So you would have to do something like K would equal 1 over the concentration of A, concentration of B squared. So you kind of do 1 over it. Obviously, if you had only products that you would include and no reactants, then it's really not a fraction at that point. It's just the products part of it would be the only thing that you would use. Any questions on that there? All right, so let's take a look at a little calculation here. The equilibrium concentrations between carbon monoxide and chlorine are 0.012, 0.054, and 0.14. We want to calculate both the Kc value, what the actual number is, and the Kp value. So take a few moments, see what you get there. Okay, so let's take a look. In this case, it would make sense to go after which one first, Kc or Kp? Kc, since we got concentrations, right? So since we're given concentrations, it makes sense to go after that. So we'll start with our expression. That's going to be our products here divided by our reactants. And since these are equilibrium concentrations, we're good basically just to plug in, and that will give us 0.14. We got like 0.012 and 0.054, I think. All right, so that will get us here a number about a 216. I don't know, a 220 if you like sig figs, I suppose, right? Since there's two everywhere. Somewhere in that ballpark as our Kc value, right? Any questions on that calculation there? Now that we have the Kc value, we could use our equation there to convert it over to our Kp value. Here, we would want maybe the delta N in this case. So that is one gas molecule there on the product side. That's one gas molecule, two gas molecules. So it looks like -1 here, or -1 is our delta N. Our temperature as well, we do need to get it into Kelvin, so a little 273 addition there, right? And that's going to get us a 347 Kelvin. Now I think we got everything we need. We could go in here. Your call, whichever number you want to go with. We'll go with maybe the rounded one. I don't know. 206. We got like a 347. We're going to take that to the -1. So times 0.08206, 1 divided by that, times it by 220, and you get like a 7.7 perhaps. Obviously, if you went with the 216 number, you got a 7.6, pretty close. We'll take either one, to be honest with you. It'll be all right. Any questions on that there? Large or small value? Okay, for these guys. Mainly reactants or products? Products, yeah. And again, you can see here that this is very typical of the case. Both the Kp and the Kc value are not the same numerical value, but they are both considered large values. And again, the both would tell you that you mainly should have products at equilibrium. Question on that one there. All right, try this one here. I don't know. We'll go with, we'll make this one NO2. How's that? Why not? I feel like there's a 2 missing somewhere. Take a look. So obviously in this case, we're giving some equilibrium pressures. So Kp would probably be a good thing. And we're also given the Kp value here. Kp value is a 158. So our expression here would be, again, our product. So partial pressure, we do need to square it because of the 2 of NO times the partial pressure of O2. Again, the coefficient there is 1, so you don't have to worry about it. Here on the bottom, partial pressure squared of NO2. Once again, we do need to take that 2 into account there. So that's going to equal 158. So they gave us some pressure. And the NO there is 0.27. We do need to square it. We're looking for the partial pressure of 2 in this case, divided by our NO 0.4 also squared equals 58. So I'm basically going to multiply that to the other side. And when I'm done with that, I'm going to take this guy and divide it to the other side, right? So we're going to go 158 times 0.4 squared. We're then going to divide it. By the way, that gets us something like 0.2 squared pressure O2, 25, 28. Again, we're going to divide this guy now to that side. We'll divide it 0.27 squared. Going to get us a partial pressure of O2 of about 347. This will need units since it's a pressure, right? So we'll have the same units as everybody else, which is atmospheres in this particular case. Question on that. So here we can see that we have a Kp value of 158, which is a fairly large value, right? Which means we should have a lot of products at equilibrium. And that would include our O2, which is a product, which obviously is supplying a good amount of pressure in that particular case. Any questions on that there? All right. I think it's a good place to lay it up here.